So quality check of your ANOVA models. You remember that when we apply ANOVA, before we applied ANOVA, we had several assumptions. First of all, we assumed that residuals are normally distributed. That's important, right? Because the whole ANOVA is built on top of these normal distribution ideas. The second assumption was that the variance in all groups are equal. And then there is a third assumption that I haven't written here, is that all factors are independent. So it means that there is no confounding among the factors. So this is also important. Okay. Now, how to check these two assumptions? How to check that your ANOVA model is valid indeed? Well, strictly speaking, you need to check the normality of your residuals, and then you need to check the equality or homogeneity of variances. And these are possible tools. You remember that from statistics, you can check normality visually by, for example, using a QQ plot, quantile normal probability plot, or you can use normality test. Usually we use both, one for visual inspection and one for kind of giving some number, some statistic. You can check variance using box plot, again for visual inspection, and then you can make a test for homogeneity of variance in order to make sure that you indeed, the difference in variance that you observe is just by chance. Okay. So let me show you quickly how it works. Well, first of all, you remember, so this is my previous example. This is what I did in ANOVA, and this is what I will be actually using for the case. So if you have R in front of you, I recommend you to pause this video and run this example, make sure that you have the same outcome, and then continue. So the first thing is how to check the normality of residuals. If I go back and show you this part, so let's look at this part, you can see that I saved my model, my ANOVA model, to a little variable m. So all outcomes of the ANOVA model, all calculations, all statistics which ANOVA does, it's located in this variable m, which is a list with different fields, right? So for example, you can see I use summary m to show you the results, right? And this m contains a lot of things, including residuals. So this last matrix that I showed you in my previous examples, everything is there. So this is how to get the residuals. If you write $m residuals, you will get the residual values. And then you can simply use a function in R that makes a cuckoo plot, the normal quantile normal probability plot. Here you have theoretical quantiles, the z-scores. Here you have the real values, right? The residual values. And then you can see that this is the line, this is ideal line, right? Then you can see that all of our points are pretty close, pretty close to this line. So it means that visually we cannot actually see any problems here. We don't have any outliers. We don't have any strange behavior of these points like groupings or maybe some funny shapes. So in this case, it seems like the residuals indeed normally distributed. How to check this even better? We can make a normality test. For example, you can use one of these Shapiro tests. It's called Shapiro-Wilk test. It's one of the normality tests which has a pretty high power. So the null hypothesis in this case is that indeed residuals came from normally distributed population. And then we compute a statistic, not V, but R. And then this is the p-value. You remember the p-value tells you how big the chance is to get values as extreme as yours. It means as non-normally looking as you have, or even worse, so it means that they can be even worse if the population where these values came from normally distributed. You can see this is approximately 90% chance, right? So this is a pretty high chance. In this case, we cannot reject null hypothesis. So therefore, it seems like our residuals indeed follow normal distribution. At least the population they came from is normally distributed. So no problem from this point of view. Now the second thing, it's the homogeneity of variance. The idea is that you remember that we have this assumption that the variance in all populations, for example, if for one factor we wrote it like this, are the same. In this case, it's standard deviation. For the variance, I need to do it like this, but it's the same. It's identical, right? And now, how you can check it? First of all, the idea is that you can check it also for residuals, because you remember that in original values, you have something on top of it. It's average values. Residuals is where we subtracted the average values, we subtracted all systematic variation, so therefore we will check it for residuals. Then you can see visually, we should see that the variation of this value should be the same. So it means that the boxes should be more or less identical, and this is what we exactly see here. Here you can see we have a kind of a bit of discrepancy. So maybe this one is not equal, right? Now I have a little cheating here. Because strictly speaking, I have two factors in one factor I have 3 groups, in the second factor I have 2 groups, 2 levels, so I have 6 different populations. So strictly speaking, I have to check the variance, equality of variance or homogeneity of variance for all 6 populations. But unfortunately it's not possible here because I have only 2 values from each population, so it's not enough. So therefore I use this workaround. I check separately homogeneity of variance separately for every factor. So what I'm going to do, I'm going to make a test. And again, like in normality tests, there are many different tests that you can use for checking homogeneity of variance. Every test has its constant pros. So in this case, I use what is called Fleener test or Fleener-Killing test. But there is also Bartlett test, Levine test. There are many tests that exist. Fleener test is quite fine in terms of power, for example. Then you can see that if I check the variance, homogeneity of variance for the first factor, it's a catalyst with 3 levels. You can see the p-value is quite large. So it's this one. And then you can see that even though we see this small discrepancy here, you can see that the p-value is also quite large here. So we cannot reject null hypothesis, which is that the variances are homogeneous. So in this case, both quality checks pass, and then we can be sure that our results are reliable. Okay. But let me show you what can go wrong. Okay, you remember, so this is the last example that I used. It's absolutely the same example. Okay. But what if, for example, I kind of forgot to use one of the factors? For example, I forgot to use factor number 1, and I make a model using only one factor, factor 2. So this is my model. You can see that y depends on factor 2, which is a temperature, and I forgot to take into account that I have also different catalyst type. So in this case, suddenly this effect of the temperature is not significant anymore. Just compare the p-values, this one and this one. But what happened? Why it went wrong? Because you remember you split your data as sums, right? So it's a sum of systematic part plus systematic part plus error. And then if you don't use this as a systematic part, this comes to the error. So strictly speaking, now in this case I have x equal to m2 plus e, but the e is in fact, it's e, the real residuals, and then also the systematic effect from the catalyst. So I artificially increased my residuals by just not accounting for the systematic part from the first factor. And you can also see it here. So this is the sum of squares for the systematic part of the first factor, and this is the residuals for the full model. Now you can see this is the residuals. So this value, it's simply a sum of these two. So because I forgot to use a correct ANOVA model, which takes into account all systematic factors, now I got the wrong result, because now the systematic variation is accounted for the random variation, and therefore the p-value is very small. So how you can check it? And sometimes you can see it by just looking at the residuals. For example, in this case, if I make a plot for this case, for this model, make a plot for residuals, cuckoo plot for residuals, you can clearly see that you have like groupings. These are 3 groups, which caused by using 3 catalysts. You will see this effect only if the systematic variation is really large. Sometimes residuals do not reveal this kind of problems, but it's always a good idea to check the residuals anyway. So sometimes if the problem is severe, you can actually reveal it by just looking at the residuals plot. Okay. So checking the quality check of ANOVA model is very important. Make ANOVA model, make a quality check, and then make conclusions if the quality check is passed. So that was almost it about how to analyze statistically more complicated experiments where you want to test influence of several factors, and some of these factors may have more than 2 levels. However, you can see that ANOVA tells you only one thing. It allows you to reveal the reproducible effects from different factors, but it doesn't tell you how big the effect is. So it tells you if a factor is reproducible, if it's significant, statistically speaking, but it doesn't tell you how big the effect is. If you want to find the size of effect, you need to do one more thing on top of the ANOVA, and that's what we are going to talk about in the next video.